Professor Brinton here, episode 3 of the Note Card Review. Topic today is polarity and electronegativity. This topic often comes back to haunt students throughout the semester because they don't get it early on. It essentially is a game of sharing electrons. Essentially, you have some elements that are much stronger in their pull on electrons. They are highly electronegative. Two things that are particularly good skills to have related to this topic are identifying particular functional groups that are either polar or nonpolar, because this will help you identify whether amino acids, for example, are polar or nonpolar, or ionic. And second, looking at a group of elements, group of atoms that are bonded together either into an ionic compound or a molecule, and determining what you're dealing with for electronegativity. Simplest situation, if we're starting here with KCl, potassium chloride, is that you end up with an ionic bond. Ionic compounds, ionic bonds do not share electrons at all, they simply steal electrons. So what you actually end up with is not a molecule at all, you have two ions. Potassium is weak in electronegativity, so it loses its electrons. Remember, electrons are negatively charged. Chlorine is very strong in electronegativity. It is able to steal the electron, and so it becomes negatively charged, an anion, whereas the potassium here is the cation. Okay? So we had one electron that was moved from the potassium to the chloride. This is ionic. Okay? This is not what most people struggle with when we're dealing with electronegativity. What you need to know more about is when you have covalent bonds. All of the rest of this is dealing with covalent bonds. Simplest situation is when you have two atoms of the same element. Nitrogen and nitrogen, two atoms, they are going to share perfectly equally. This is a nonpolar bond. No pull, no tug of war between the two atoms, they simply share. If you were to actually bond two nitrogen atoms together, you would end up with a triple bond, and you would have 3 pairs of electrons in here being shared perfectly down the middle, moving around each of the two atoms at exactly the same pace. So this is a nonpolar covalent bond. Okay, so nonpolar covalent. H2O is a classic example of a polar covalent bond because you have oxygen, 2 hydrogens, and when you compare these two different elements, you find that oxygen is much more powerful, much more electronegative than our hydrogen. So in this case, we end up with uneven sharing of the electrons. Oxygen here is a hog, hydrogen loses out, so the hydrogens have a partial positive charge because they've lost control of the electrons if you compare them to the oxygen. This leaves oxygen with a partial negative charge, so we have poles, just like poles on a magnet, positive and negative, and this is a polar covalent bond. Okay. Third on our list here of examples is a much more complicated molecule. But if we walk through this bit by bit, what you can do is compare the atoms in particular bonds and determine if they are going to share electrons evenly or not. Let's look at a couple pairs. If we have this carbon bonded to one of these oxygens, oxygen is more electronegative than carbon, so it's going to win out. The oxygens in general are going to end up with partial negative charges. Oxygen is a hog in organic molecules. You are frequently going to see polar molecules with oxygen in them. Hydrogen is generally our loser. It's the weakest of them. However, its weakness is comparable to carbon's weakness. So if we compare carbon and hydrogen, if, say, we had a methyl group with a carbon, and actually that's right over here, carbon and 3 hydrogens bonded to it. Okay, got this drawn out in a variety of ways. This is a bond that is close enough to share perfectly that all of these are nonpolar covalent bonds. Oxygen, that hog that I mentioned, is particularly strong, often can form double bonds with other compounds, and it is going to hog control of these electrons. So this is, each bond is representing 2 shared electrons. Those electrons are going to spend much more of their time over here towards the oxygen atom. If you're looking at a molecule or any sort of illustration for a particular compound, such as for an amino acid, look for these common regions that are very polar, like a double bond to an oxygen here in this carbonyl, or regions that are going to be nonpolar, such as these carbon-hydrogen bonds here.